So, as I was just saying, I talked to some people in the class, and I think we thought it'd be best if we had quizzes on Wednesdays instead of Tuesdays. So, if anybody is not in class right now but watching the video, there's a heads up for you. If you skip class on Tuesday, you didn't get out of the quiz. So there's that. We're going to have them on Wednesdays. I'll change things to reflect that in the assignment schedule, but for now, just try and remember that. Tomorrow, we're going to have a quiz on just basic rules of exponents. It's totally okay to write those rules on a note card and bring them into the quiz. I know that seems a little too easy, but it is not. I just want to make sure you know how to use those. Okay, so in the previous two classes, we went over exponents and all their rules and all that stuff. I'd recommend that you try to memorize those if you can. If not, always have them next to you when you're doing your assignments. In this chapter and the next, we're going to go over polynomials, the basic definitions and things like that, and then we're going to do some addition and subtraction of polynomials, which can be a little bit repetitive. But that doesn't mean we don't get to go over it. So let's go over some definitions to start out with. Remember the definition of a term. A term is what is separated with addition or subtraction in an expression. So this first expression has exactly three terms. Those terms are 3x squared, negative x, and 2. Each one of those is a term in the overall expression. So a term that is a product of constants and or variables, that is called a monomial from now on. We still call it a term, actually. But it's also a monomial. All right, and so when I say product or constants of variables, remember that product doesn't include division. And so when we have an x underneath the denominator, we don't really call that a monomial. It still could be called a term, though. Okay, these are all monomials. 3x, that's a monomial. 2, that's a monomial. X to the 33, 22x squared, y cubed. Those are all monomials. Now, a polynomial is just a collection or a sum of monomials. Okay? So, a polynomial, basically all monomials are also considered polynomials. Okay, so a monomial means one. Polynomial means many, but even if you just have one, it's still considered a polynomial. This is an example of a polynomial. This is all those monomials we just mentioned summed into one. Okay, and each monomial in this overall polynomial, we still call those terms. So in some examples, we're asked to identify the terms of the polynomial. So to do that, we just list them below. So remember the term, the negative sign comes along with the term. So if we're listing terms for this, we have 3t to the 4th. The term is negative 5t to the 6th, negative 4t, and 2. Those are all the different terms in this polynomial. Okay. Oh, sorry. Thank you for letting me know. So, notice, is that too fast? Good, okay. So, not notice, but next, a polynomial with a single term is known as a monomial, like we just went over. If it has exactly two terms, we call it a binomial. If it has exactly three terms, we call that a trinomial. All right, so a monomial is like x squared, that's a monomial. A binomial would be like x squared minus 1, because that has two terms. A trinomial would be something like x squared plus 3x minus 1, because that has three terms. As we go along in this class, kind of one of our next focuses we'll be solving things like this, trinomials and binomials, soon. Okay, let's go over degree. So the degree of a monomial is the total number of variable factors in that monomial. And that means variable factors. It doesn't matter if one's an x and one's a y, they both go into the total, right? And so this one has 4 factors of x in it. So this one, the degree of this monomial is 8. Not 8, I'm sorry, it's 4. I was reading the coefficient. It's 4 because there's exactly 4 variable factors in here. For this one, 3x, the degree of this is equal to 1, right? Because there's exactly 1 variable factor involved. When we're just dealing with constant terms, the degree of this is equal to 0 because there's no variable factors involved. Okay. Make sure you guys don't write the equals sign right after this. Like if I say, what's the degree of this term, this d term, and the degree is 2, don't ever write it like this, because that doesn't equal 2, right? The degree of that term is 2. It's completely incorrect to write an equals sign after that. I usually write a little arrow that says, yeah, this is related. The degree of this monomial is 2, because it has exactly 2 variable factors. All right, the degree of this one, remember, it doesn't matter if they come from different variables. There are 8 factors of y, 2 factors of x. Whoops, I almost did exactly what I told you guys not to do. So put those together and we get the degree of this is 10. And really, like the proper notation, not that I'm never going to ask you for that in here, but if you want to be proper with it, you would say the DEG of, and you put your monomial in question inside the parentheses. You'd say the DEG of x squared y to the 8th is equal to 10. That's when it's appropriate to use the equal sign. But this is just fine for now. For now. All right. What about this one? What's the degree of f? Think about it. I put this out to mess with you guys.
0.
It's 0, yeah. You think, right, you want to say 1 immediately because you see x there, and you say, well, x is a variable, but the only value that this variable can ever take on is just 1, right, because it's x to the 0. Yeah, so since x to the 0 equals 1, and the degree of 1 equals 0, the degree of this guy is also equal to 0, okay? So that's what we call degree. Alrighty, and I know we've gone over this before, but let's review this definition. So the part of the term that is a constant factor, that's called the coefficient, right? And so when we talk about the coefficients of this polynomial, we talk about the coefficient of each term. This, the 4x cubed, that has a coefficient of 4. Negative 7x squared, that has a coefficient of negative 7. Can anybody tell me what's the coefficient right here on the x? 1. Yeah, don't forget that. That has a little coefficient of 1 down there. And then the coefficient of this last term is just itself. All right. So, more definitions. The leading term of a polynomial, that's the term of the highest degree. And its coefficient, that's called the leading coefficient. So when it comes to this polynomial that we just went over up here, this term right here highlighted in blue, that's the lead term because it's the term of the highest degree, which means the leading coefficient of this polynomial is 4. The degree of the leading term is the degree of the entire polynomial. All right, so the degree of this whole polynomial is 3. Okay, moving on. Okay, so that leads us to how to combine like terms. So when we're talking about combining like terms in like a larger polynomial, you can combine like terms, similar or like terms are defined as terms with the exact same variable factors. Oops. And by exact, I really do mean exact, the same number and everything. So I've just kind of lined up on the left side are examples where we do have like terms. On the right side are good examples of when we do not have like terms and we can't add them together. So this one here, 3x and negative 4/3 x, I could add those terms together because they both have exactly a variable factor of x. These two terms I'm not allowed to add together because one has a variable factor of x, the other does not. All right, this next example, 42x to the 5th and 2x to the 5th, I can add those together because they have the exact same variable factors. And I just add their coefficients. These ones over here on the right side, though, you can see I have an x to the 4th on this 33 and an x to the 5th on the 11. Since the number of variable factors are slightly different, we cannot add those together. Okay, 3xy and pi xy, those are like terms. They have the exact same. This is an important example. A lot of times, they'll try and mess with you a little bit, right? Notice how both of these are degree 3, so they have the same degree, but on one there's 2 variable factors of x, where on the other there's only 1 variable factor of x. That's not allowed, so they're not like terms. Okay? So, in these next examples, we are just combining any like terms. So in this example A, I see that these have the exact same number of factors of x, so I'm allowed to add these. So I just add their coefficients. 6 plus 2 is 8. So I have 8x cubed. Notice that this little cube term, this does not change. So be careful with that, right? We're not multiplying, we're adding. Right, in this next example, when I get a big, long list of junk like this, I like to go through and just sort of slowly pick out the highest degree term and work my way down from there. Right, and so I'm looking at all these terms. I see that I have 4th degree terms here and here, so I'm going to take care of those first. 2x to the 4th minus 2x to the 4th, those actually cancel each other out. So I'm going to cross them out to let myself know that I've already handled that, right? And so now I'm going to look for the next highest degree term. I have a 2nd degree term here and here, but those are the only two, so I'm going to add those together. So I have 5x squared minus 6x squared. That gives me a negative 1x squared. I'm going to cross those out so that I don't confuse myself. Now I only have my 0 degree terms. I have a 7 and a negative 11. 7 minus 11, that gives me a negative 4. Okay, so that's what I look like after I combine all those like terms. In this chapter, you're going to want to kind of give yourself a little bit of an organizational method. You know, like I go through a pretty simple one. I start at the highest degree. I cross everything out after I use it. You're going to want to create something like that for yourself because all this stuff, it starts to get a little jumbled up in these next few sections. There's a lot of terms. So let's try this again. So I have, it looks like a 3rd degree term is my highest. So I'm going to handle those first. So I have 9a cubed plus 7a cubed. That gives me 16a cubed. Cross those out because I already dealt with them. Now I just deal with my 2nd degree terms. I have an a squared minus 5a squared. That gives me negative 4a squared. And that's it. I've handled all the terms, so I'm done. I hate this one. Okay. Just because they're fractions doesn't really change anything, right? We still match up like terms, right? And so it looks like we have 2 4th degree terms that we can add together. And then we have a bunch more 3rd degree terms. So I'm going to write those 4th degree terms out first, and we're just going to start handling them one at a time here. So I have 2/3 x to the 4th. I'm going to say minus 1/6 x to the 4th. All right, so since I'm dealing with fractions here and I have quite a few in-between steps, first I'm going to organize everything so it's next to each other, and then I'm going to start combining fractions, okay? So I'm going to organize those so they're next to each other. Then I need to organize my x cubed terms. I have 1, 2, 3 of those, so I'm just going to line them all up. So here I have, we're going to call this plus 2/5 x cubed minus 3/10 x cubed, and then we have just minus x cubed. All right, so I need to combine my fractions on my 4th degree terms. You guys will remember from fractions, I need to make these two denominators match before I can add them up. So this first fraction, 2/3, I need to multiply top and bottom of that by 2. And that way I can get matching 6 in my denominators. So I have 2/3 times 2 times 2 x to the 4th minus 1/6 x to the 4th. Okay. So now I'm going to keep doing the same thing, but with my x cubed terms. Right? So my denominators for this are 5, 10, and 1. So I know that my common denominator is going to be 10 with this second set of fractions. So I need to multiply top and bottom of this fraction by 2, and then top and bottom of the coefficient of this one by 10. So I have plus 2/5. I need to multiply top and bottom of this by 2. I know this is a big problem. It's ugly. X cubed minus 3/10 x cubed minus 10/10 x cubed. All right. So now in this step, we can combine things. All right. So, and maybe I'll just simplify it all in this step. So on this, I have 2 times 2 over 3 times 2. That gives me 4/6 x to the 4th minus 1/6 x to the 4th. I'm adding this to 4/10 x cubed minus 3/10 x cubed minus 10/10 x cubed. Okay, now I just need to combine things finally. So I have my coefficients on my x to the 4th terms. 4/6x minus 1/6 x. That gives me 3/6 x. That's a tongue twister, which is 1/2 x, right? 3/6 is 1/2, so I have 1/2 x to the 4th. That's what I get from combining these two. And then with this one, I have 4/10 minus 3/10 minus 10 more tenths. So I have 4, let's see now, minus 13. Is that negative 0? No, it shouldn't be 0. It should be 4 minus 3 minus 10. So it should be 4 minus 13 on the top, which is negative 9, right? 4 minus 13, negative 9. So we get a negative 9/10 right here, x cubed. And that's it. That was great, right? You guys want one like that on your exam? No, I wouldn't. This would be something I might put on like the final exam maybe, but not on this upcoming exam. All right. So now let's talk about evaluation when we do polynomials. It's just plug and play. It's exactly like we've done before. You're just plugging into a polynomial instead of like a formula or something like that. So when we talk about evaluation and they give you a polynomial and a value for the variable in that polynomial, we just plug it in and calculate. So my negative x squared turns into a negative minus 2 squared. My plus 3x turns into a plus 3 times negative 2, and my plus 9 just stays as plus 9. So my negative 2 squared, that turns into a positive 4, but this negative out here maintains the negativity. So I have negative 4 overall, minus 6, because 3 times negative 2 is negative 6, and then plus 9. What does that give me? Negative 1. Boom. Okay, so you just plug it in. And remember, if it's a negative number, be careful with your parentheses. Right? Put the parentheses around it every time you plug it in just to keep it straight. So here's this beast right here. So this is also something this is definitely something that you could see on an exam, right? With evaluation problems, because they're just plug and play, sometimes I like to give you evaluation problems, and not just me, the book does too, that are super ugly. They're just the most ugly thing you've ever seen, but if you just calm down, plug stuff in, and put it into a calculator, you'll be just fine. So this guy here, they say this is an equation for the number of watts of power, P, generated by a particular wind turbine at a wind speed of X miles per hour. So the wind speed is X. This can be approximated, whoops, I think I just said that again. Estimate the power generated by a 10 mile per hour wind. So there's two ways to sort of handle this. We could start plugging in 10 for X and then make this into a big ugly equation, or we could just remember that for each factor of 10, we move the decimal place over 1, right? And since this first one, this is 3 factors of 10, right? It says multiply this very small number by 10 3 times, which essentially means we move the decimal place over 3 times, right? And so we drop the X because that was what we multiplied in, and this first term turns into 15.7. The second term, this one's multiplied by 10 twice. So we move the decimal twice, 1, 2, and this gives us 11.63. This third term, it's only multiplied by 10 once, so we only move the decimal once, minus 13.396. And the last term, there's no variable there, so it just drops straight down, plus 3.7063. This is definitely one for the calculator. I'm not going to do this on paper. That would just waste everybody's time, I feel like. When you run into something really ugly like this, it's always good to punch it into your calculator at least twice, if not 3 or 4 times. I don't know how many times I've seen people punch this into their calculator and get one little thing wrong and just accept that that's their answer. You know, and it's tough to go back and correct for that, you know. And so this gave me 17.6403. I'd want to check that at least one more time just to make sure I got the same exact answer so that I didn't make some random error when punching all this in, because it's a lot of different stuff to punch in. All right, so there's that one. This is the function behind that ugly polynomial. In this problem, they give us the graph of the function and they say, use this graph to please estimate how much power is generated by a 30 mile per hour wind. Well, to do that, we just zoom way in on this graph. And then we go down to wind speed, which is on our x-axis, and we pick out 30. That's right here. We follow a vertical line from 30 until we hit that graph, right about here, and then we follow that point horizontally over to the corresponding y-axis. Looks like about 500, right in between the 600 and the 400 right here. Right, and so we would say P equals 500. Or since this is an application problem, we would say the amount of power generated by a 30 mile per hour wind is approximately 500 watts. Wow. That's an interesting function. I haven't really noticed this before, but look, check out how weird this function is, right? How much of a difference that extra wind speed makes. At 10 miles per hour of wind, we're generating like 17 watts. That's super weak sauce, right? Which I'm not an electrician. Maybe that's an awesome amount of power, but it doesn't seem like much, right? 17 watts, wah, wah. But if we get 30 watts, right, we're tripling the wind, but we're multiplying the amount of watts we get by like 20, right? That's what it means to be an exponential function. if somebody ever says the word exponential, this is increasing at an exponential rate. This is what they mean. They mean it doesn't increase 1 to 1, and so 10 equaling 17 doesn't mean 30 miles per hour wind will give you 3 times 17. It increases exponentially, so it gives you like 20 times 17. All right, so there you go. Okay, so that is 4.3. Now let's go into the most exciting chapter that we're gonna go over all semester. And this is a chapter about addition of polynomials. When I say exciting, that's a joke. This is not very exciting. It's pretty straightforward. The thing that will really trip you up is just like I said earlier, you might want to create a little system for yourself just to organize your work so that you don't lose track of terms. That's the easiest thing to do on these problems. So when I talk about adding polynomials, if they give us 2 polynomials and they've put them in parentheses and the operation in the middle is a simple addition, the parentheses basically don't matter. We can just forget they exist. The times when the parentheses do matter is if there's a negative in the middle here, and we'll go over that in a little bit. But for this first one, we just drop the parentheses and add everything up. Okay, so I note I have a positive in the middle, so I don't need to mess with the parentheses at all. So I just add the terms as they appear. So my highest degree term is a 3rd degree term. So I have a negative 5x cubed plus 4x cubed. That gives me a negative 1x cubed. I'm going to cross those out so that I don't confuse them later on. Next, I go to my square term, right? That was a 3rd degree term, so now I need my square terms. I only have one of them, so that's it. It drops straight down. Plus 3x squared. Cross it out. Now I have my single degree term, the one with only one variable factor. That's the only one that appears in the problem, so it just drops straight down too. Plus 6x. Cross it out. Now I have my 0 degree terms, negative 1 plus 2. Of course, when I add those up, I get a plus 1. So I'm not sure if I don't think I mentioned this earlier, but the proper way to put a polynomial is what they call in descending order, and that means your highest degree term goes out front. I'm not a huge stickler about this, but it's going to help you out later on to get in the habit, because that's the way a lot of our formulas set up, with the highest degree out front. So that's typically the way you should write it. All right, let's add this guy together. It's the same thing as what we just did, except with different terms. So my highest degree term, it looks like, is a degree 3 term. It's right over here. I don't see any other degree 3 terms, so it just drops straight down. My next ones would be my degree 2 terms. I only have 2 of those, so I'm going to add them together. I have x squared minus 3x squared. That gives me a negative 2x squared. Cross those out. Take a look at my single degree terms. 7 minus 3, that gives me a plus 4x. And then I have my 2 minus 5, which gives me a negative 3. Okay, and that's it. So we're going to go over the column form. I don't ask you to really learn this. You might have a homework problem that asks you to do it. It tends to be like a very tedious and time-consuming way to add things together. So it just helps to remember that we can do this if we want, but in the end, it's pretty awkward, I would say. So the weird thing with adding things in the column form is that we need to put in placeholders. And so what I usually do is I pick out whatever polynomial has the highest degree term. I'll put that on top, and that makes sure that I leave room for everything else. So this one has a 6th degree term, so I'm going to put it on top. So what you want to do is you want to write out your polynomial and keep it organized so that you don't kind of lose track as you keep writing them vertically. But you go ahead and you write your polynomial, 5x to the 5th. But this is the part you got to remember, is that you got to put in placeholders where there's no degree in that place. And so I don't have a fourth degree term here, so I have to write plus 0x to the fourth. And that's why this is so tedious, is because you have to put in placeholders for all the things you're missing. Okay, so I don't have a third degree term over here either, so I'm going to say plus 0x cubed. I do have a squared term, so I'm going to say plus 1x squared. And I have, oops, I do not have a single degree term, so I have plus 0x. And I do have a constant, so I say plus 5. Okay, so now I line up all of my other polynomials underneath this one. So I'll write out this guy next. So I have 0x to the 6th plus 0x to the 5th plus, I do have an x to the 4th term, so it's plus 5x to the 4th plus 0x cubed minus 7x squared plus 0x plus 6. And then we keep going. I don't have a degree 6 term, so I have 0x to the 6th again. I finally have a 5th degree term, so I have plus 9x to the 5th plus 0x to the 4th. Whoops, that should be a negative. You can see how ridiculously tedious this is. Minus 2x cubed plus 6x squared plus 0x plus 3. When I thank you for your patience today, I'm really going to mean it. All right, so now I add vertically. So I draw my line and I just add the columns as they go. So my x to the 6th column, I have 3x to the 6th and nothing else, so that drops straight down, 3x to the 6th. In my x to the 5th column, I have a 9x to the 5th here and a negative 5 here, so that leaves me with a plus 4x to the 5th. Those ones are done. I only have 1x to the 4th term, so I have plus 5x to the 4th. Those are done. Minus 2x cubed. These are gone. In this column, I have 3 different terms I'm adding together. So I have, let's see now, oh, but they cancel each other out. 1x minus 7x plus 6 more x. That gives me plus 0x squared. Nothing here. And then finally I can add up my constant terms. 5 plus 6 plus 3, that gives me plus 14.
You still have that single x term in there?
You don't, and I didn't even need this term if I didn't want it. Yeah, it's, you put in the placeholders up top, but you don't need them once you do the final addition. So you can certainly do that. But honestly, like if I wanted to just add those 3 polynomials up, I could have done it in maybe like 10 seconds, 15 seconds. That took me a few minutes, so it's not very convenient. So there's that. Let's talk about opposites. So the opposite of any polynomial p is just negative p. Right? And so the opposite of this ugly polynomial here is just that same polynomial in parentheses with a negative out front. Okay, so when I say the opposite of a polynomial, I mean we just multiply that polynomial by -1. That's it. So in this example, they ask us to write 2 equivalent expressions for the opposite of the following polynomial. All right, so first we're going to write our first equivalent expression. We know that to create an opposite, we just put parentheses in there and put a negative sign out front. So I'm just going to say, okay, negative in parentheses, and then repeat the polynomial. 4x to the 5th minus 7x cubed minus 8x plus 5 over 6. Okay, so that's one equivalent expression. Let's write the other one. And so to write the other one, we just distribute the negative in front. That's it. And so I distribute that negative to the positive 4x to the 5th, and that turns into a negative. Right? And this is all I'm doing, is kind of distributing this negative sign in to create this other equation. All right? And all it does is change the signs on the coefficients. So my negative 7x cubed becomes a positive 7x cubed. My negative 8x turns into a positive 8x. And my positive fraction turns into a negative fraction. Okay, so those are two equivalent equations for the opposite of the original polynomial. They've asked me to simplify this. I can't really combine any like terms, otherwise I might do that first. But to be fully simplified, we don't really want like a negative out in front of parentheses. We want to distribute that in. So I'm going to go ahead and do that. So I just switch all the signs on my terms. This turns into a positive 7x to the fourth. This turns into a positive 5 over 9x cubed. This turns into a negative 8x squared. My negative x turns into a positive x. And the sign switches on my constant term as well. Okay, so that's it. When they ask you to simplify something like that, it just means you distribute the negative. So that leads us to subtraction of polynomials. So the only difference between subtraction and addition of polynomials is that before you do subtraction of polynomials, you have to distribute this negative sign first to get rid of these parentheses. Otherwise, combining all your terms doesn't work. So on the very first line, when we're asked to subtract polynomials, we just distribute the negative. So everything in the first polynomial stays the same. Everything in the second polynomial switches sign. So negative 2x to the fifth, that's positive now. I have a positive 4x cubed now instead of a negative. And everything just switches. All right, now that I did that, I can just go through and collect any like terms that I can. So I have a couple of fifth degree terms, 9x to the fifth and 2x to the fifth. That gives me 11x to the fifth. I'm going to cross those guys out. Looks like I have only one fourth degree term, so that drops straight down. I have 4x cubed and a plain x cubed, so I can add those together to give me plus 5x cubed. And my second degree terms, I have two of those, so I can combine them. Negative 2x squared and 3x squared, that gives me plus x squared. And I do not have any single degree terms. I only have one constant term left, so that drops straight down. Okay, so that's it. To subtract polynomials, you just apply the negative and then combine like terms, and then you're done. All right, so so how about you guys try that out with this next example? I know you guys are bored out there. Go ahead and try this guy out. All right. So for this guy, on your first step, you should have applied this negative sign to the second polynomial. So the first one just drops straight down. 7x to the fifth plus x cubed minus 9x. And then we apply this negative sign to each term. So that gives me a negative 3x to the fifth, positive 4x cubed, and then a negative 5. So now I just go through and I combine my like terms. So I have two fifth-degree terms, 7 and negative 3. That leaves me with 4x to the fifth. And I have two third-degree terms, x cubed and 4x cubed. That leaves me with a plus 5x cubed. Oops, I should have crossed these ones out. And then I have a single x term with just one x, so that drops straight down, minus 9x. And then I have a constant term, negative 5. Yeah? You guys nailed it? Bravo, bravo. So, I will note right here, subtraction can also be done using the column method. I'm just gonna state that. I'm not gonna demonstrate. It's done the same way though. You just apply the negative sign and then add vertically. Okay. Here we go. So the first problem. So in this example, we're asked to find a polynomial for the sum of the areas in these rectangles, A, B, C, and D. So they say find the sum of the area, right? And so we're saying the area of A plus the area of B plus the area of C plus the area of D. That's what they want. We're going to say equals total. So we can come up with smaller equations for each one of these smaller rectangles and turn those into a larger polynomial. Okay, so you know to find the area of a rectangle, it's just length times width. And so if the sides of my A rectangle are x and x, what's the area? Yeah, I know you guys knew it, you just didn't want to say it, right? I know that feeling. Okay, yeah, it's just x squared, right? X times x. Right, and so when we look at the area for my B rectangle, this one right here, I just multiply the sides. I have a side of 5, and over here I can see I have a side of x. So this is plus 5x for B. C, that has sides of x and 2. So I say plus 2x for C. And finally, I have my D all the way up here in the corner. And that one has a side of 2 and a side of 5. So I say plus 2 times 5, which is 10. That equals my total. I'll call it T. All right. Now, finally, of course, I just want to combine like terms. We always want to do that, so everything's completely simplified. So the area of the larger rectangle is represented by x squared plus 7x plus 10. Okay. So, one more example here. So in this example, a 16-foot wide round fountain is built in a square city park that measures x feet by x feet. Find a polynomial for the remaining area of the park. Okay. So let's draw a diagram first. We have a square park, sort of square anyway, and we have a round fountain in the middle, and they say this fountain is 16 feet across. And they're talking about the area of these two things. They want us to create a polynomial for the remaining area of the park without the fountain. Okay, so they want this area only out here. Okay, we have sides of x. Whoops, where's my pen? Uh-oh. Did my pen just crap out on me? No. Okay, so we have sides of x here. All right, and so the total area of this whole park is just x squared. That's the total area, but that's not what they wanted. They wanted x squared, the total area, minus the area of this circle in the middle. So we need to figure out what the area of that circle is. The area of a circle is just pi r squared, where r is the radius of the circle. So if you guys haven't studied geometry in a while, that's totally okay. But what we're looking at here, this number 16, that's known as the diameter of the circle from edge to edge. The radius is the point from the direct center of the circle to the edge, right? So that is half of the diameter. So in this case, our radius is equal to 8, right? So we're going to say x squared minus pi r squared. And now all we need to do is fill in what r is to get our final polynomial. So I have x squared minus pi times 8 squared, which is just 64. So the polynomial for this is x squared minus 64 pi. Okay, any questions? No. Thank you for your patience today. I know those addition problems are like really tedious sometimes. It's last semester I actually did the column subtraction problem, and it was terrible. It was awful.